Hi, everybody. We're going to talk about the last topic in Unit 1, Part 2, finally, today. The topic is a really important one. It is called parallax. What parallax is well, that's what we're going to talk about in this video, but it is a crucial astronomy concept because parallax is how we measure the distances to the stars. We're going to start on simpler earthly-based versions, and we'll expand it out so you can see how we can use this method for the stars. So the slides that I'm about to use are fairly different than the ones that you have in the textbook. And what I'll do is I'll post these slides in the week 4 README so you can have access to them as well. So let's talk about parallax. Let's start with what is parallax. So parallax is something that we're all familiar with, and I'll read out what the definition is, then we'll run through a little practical example of it, and I'm gonna end this video by doing an example here in my home where we can see parallax in action. So the formal definition of parallax is the apparent displacement. So something is going to appear to change its location. So it's the apparent displacement that an object will have when viewed from a distance at two different vantage points or from two different vantage points. So we have to measure this against some sort of reference that's going to be a fixed background. So what we're going to do is we're going to view something from two vantage points, say my right eye and my left eye. And we're going to see how that changes where it looks like something is going to appear. The classic example for this is you go ahead and do this with me or listen to me and then pause the video and play around with it. Go ahead and stick out your thumb at arm's length. Close one of your eyes. I'm going to close my left eye. Looking really cool while I do this. And then go ahead and place your thumb so that it covers up something or lines up with something wherever you are. I'm going to place my thumb so it's covering up the green light that indicates that my camera is on. So I cannot see the green light, my thumb is covering up, and then I'm going to switch from viewing with my right eye to viewing with my left eye. Whenever I do that, probably no surprise to anybody that now my thumb doesn't look like it's covering up the green light on the camera. And if I switch back and forth, it looks like my thumb is moving back and forth. There is an apparent displacement, an apparent shift measured against the background. And here my background was my computer screen where I could see the green light. So that shift back and forth, that apparent displacement is what we call parallax. And just like we can't measure physical distances, like how do I describe the physical distance that it appears my thumb is moving against a fixed background? You can't say, oh, that was 10 centimeters. What we can do is just like we did with angular size and separation, we can use an angular measurement. So we measure parallax and the number of degrees it appears that my thumb shifted with respect to the background. So in your textbook, you have this picture right here that demonstrates that when you view this object, this star, from viewpoint A, it would look like it's hanging out in this blue background. And when you view it from B, it looks like it's hanging out in this red background. That's all well and good, and it does a decent job. The apparent shift from the blue over to the red, from the blue over to the red, that would be your parallax angle. I wanted to do something a little bit more realistic to how things would be viewed because that does not look like how I view things. So hopefully this will help. So this is my version that I built of this. So now we have viewing from point A and viewing from point B. Here are our eyes. And we'll be viewing this star that's some distance away. So I'm observing from this location. Let me go ahead and make this full screen. I'm observing from this location right here. So whenever I view the star from A, it looks like from the vantage point of A, it would look like this blue background, this fixed background that I have built right here. So it looks like the star is in front of the blue background. But if I looked from B, it would look like it's in the red background. So two different vantage points, viewing from two different locations, and it looks like this star has shifted from A to B as I switch from looking from A to B. Now let's go ahead and put some terminology on this. So when you view from A and then you view from B, it looks like the star shifts back and forth. We measure how big of a shift it is using angular measurements. And the size of that angular shift say 3 degrees, 5 degrees, 10 arc minutes, whatever it is, just an angle is what we call our parallax angle. How much my thumb shifts back and forth, maybe 1 degree, maybe 2 degrees. So the apparent shift that we observe measured in an angle is called the parallax angle, usually just called the parallax. The distance between the two vantage points is what we call a baseline distance. This is a known distance or a measurable distance. Maybe here, what I did is I viewed it over here, and then I put down a meter stick and I walked over 1 meter and I viewed it from 1 meter away. Then my baseline distance would be 1 meter. Maybe I'm just standing there and I'm gonna do the eye blinky things and I'd measure the distance between my right eye and my left eye. And the distance between my eyes would be my baseline distance. Or maybe I'm crazy and I wouldn't look from A is over here and then 10 meters away, B is over here. It's a known distance. We call that the baseline distance. Notice if I increase the baseline distance, the parallax angle would also increase. Now let's move farther away. How does parallax work and relate to distance? Because not all the stars are the same distance away. Not all objects are the same distance away. Some objects are further away than other objects. So how will that change the parallax that we measure? So if you have your thumb out at arm's length and you blink your eyes, this time, pull your thumb in so it's about half the distance away from your face. So now it's closer, and repeat the experiment. Blink your eyes back and forth. You'll notice that your thumb is shifting back and forth a larger displacement, a larger number of degrees. And in fact, the way it works out, if I half the distance, I'm going to double the parallax. Sounds sort of familiar to this inversely proportional business. Okay, so in this one, I'm just going to scoot back from the star. So now I'm observing from farther away. My baseline is the same. I'm still viewing from A and B. And I want to see how the displacement when viewing from A to viewing from B changes. I want to see if the parallax is going to be a bigger angle or a smaller angle. So I sighted up from A. I sighted up from B. And you can see the shift right there. And go ahead and put it all on one thing. And now we can see our parallax angle is a lot smaller. I moved farther away, I increased my distance, and my measured parallax got smaller. Increased the distance, measured parallax got smaller. And my baseline distance remains the same. So now we're not only seeing that we have this effect of parallax, this apparent displacement, something appears when viewed from two different vantage points, your two different eyes, but also how much the object is displaced depends on how far it is away. Change the distance, change the parallax. And it does so in a very controllable way. You half the distance, you double the measured parallax. What this does is this is really connecting parallax, measured parallax, to the distance away. So if you have a reference point, say you know what the baseline distance is, then you can use a little bit of trigonometry and geometry, something I don't expect you to do in this course, but you can use trigonometry and geometry then, and use these triangles here to actually calculate the physical distance from the measured parallax. Very, very, very small parallax, that thing's got to be very, very, very far away. Large parallax, that object is a lot closer. And it's using this method is how astronomers are going to actually determine the distances to the stars. I know I said that without any words on the screen, so let's go ahead and say that again. And again, just to relate this to what you see in my textbook. So here is a picture that I have where I have object 1 and object 2 viewed at different distances. This is very similar to the scenario I just showed you. When viewed from A, it looks like object 1 would be here, and when viewed from B, it'd be here, a pretty large parallax angle. This object that's farther away, repeat the experiment, viewed from A, viewed from B, smaller parallax. bigger distance, smaller parallax. And it comes out that parallax is inversely proportional to distance. And I know you're still trying to wrap your brains around what it means to think proportionally, but that means as one thing changes, the other thing's going to change in proportion to it. And that means by the same multiplicative factor. The inversely proportional part means that if one thing gets bigger, say 10 times bigger, the thing that it's inversely proportional to will get 10 times smaller, become 1/10 the value. So let's run through an example. An object 5 times farther away from you. So we have an object, we measure its parallax, then we're going to move it 5 times farther away. When we move that object to be 5 times farther away, you would measure 1/5 the parallax. So now we have an object some distance away, we measure the parallax, and this time we're going to move it so it's 5 times closer, 1/5 the distance that it used to be away from you. So now it's 5 times closer, the distance is smaller, my parallax is going to be bigger. It's 1/5 the distance, it's 5 times closer, my parallax will be 5 times larger. And I know you just have to sort of play around with some of these. This is why I build these kind of questions into the homeworks. If I have time this weekend, I'm gonna try to build some practice problem sets so you can really start understanding what it means to be inversely proportional to and directly proportional to. But for now, I wanna go ahead and continue the video, because how do we actually use this in astronomy to measure distances? Because remember that the stars are incredibly far away, light years away. So as this distance becomes bigger, our parallax becomes smaller, right? That's just what we talked about. So that means for things very, 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 very far away, like the stars, this parallax angle that we're going to measure is extraordinarily small, and it's hard to measure very, very small things. For example, imagine I gave you a ruler and I told you to go measure how big a grain of salt is, and do it with accuracy and precision. A hard task. It's hard to measure small things. So what can we do? So in astronomy, the way that we're going to use this is we want to have a very, very, very big baseline so we can measure the parallax that a star has, a nearby star, against a fixed background of farther away stars. So we want to see how much it's shifting relative to the stars, the fixed background of stars that are very, very, very far away. What we want is a very big baseline. So let's use, say, the entire Earth from one side of the Earth to the other side of the Earth. Here's my object in space, and I will view it. I'll have one astronomer, one team will view this object in space from here, while at the same time, another team views the same object from a baseline of the entire diameter of the Earth. It would look like the star viewed from A to B. This is where it'd be in the A position. This is where it'd be in the B position. So you have that apparent displacement, that parallax, and the angle that it shifts would be our parallax angle. We could measure that. It's going to be very, very small, measured typically in arc seconds, in fractions of an arc second, but it can be measured. That already tells me that my angle of parallax is measured in arc seconds. Those things got to be really, really, really far away. One thing that we can do, so the baseline of Earth's diameter, sure, that's really big, right? It's not really big enough to make this method of parallax to measure the distances to the stars. It doesn't really provide a big enough baseline to do it reliably and accurately. What we want to do is use the biggest baseline that's available to us as humans. So let's increase our baseline distance. So if I made my eyes further apart, for the same distance, I would measure a larger parallax. So let's use the biggest baseline we possibly can, the orbit of Earth itself. So let's just imagine that here the Earth is in June, and here's our nearby star. Here are the fixed background, the far, really, 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 really distant stars. that you don't really see parallax because they're so far away. Their parallax is much, 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 much smaller. So I observe this star in June, and it appears like it's hanging out right here with the stars. I wait 6 months, so Earth has gone halfway around its orbit. What would be the baseline distance? Well, the distance between the Earth and the Sun is 1 AU. So we have 1 AU, 2 AU, a baseline of 2 AU. That's about 200 million miles, a little bit less, 194 million miles, or 196, sorry, million miles. That's a huge baseline. And we measure from here in December, and it looks like the stars hanging out over here. We see that small apparent shift of the stars. We measure it, and yes, it's very, very small, less than 1 arc second. But now that we have that, we can apply a little bit of trigonometry and geometry. Notice that in this one, we've drawn some nice right angles. So if you remember your SOHCAHTOA, it's as easy as that. Well, actually, these angles are so small, it becomes much, much, much easier when you do the distance calculation. You're going to apply this thing called the small angle approximation. That's for the curious. But now you could just use simple geometry and trigonometry to calculate what this physical distance is that gave us the parallax that we observed. And just to show you how hard this is, our nearest star, Proxima Centauri, has a tiny, tiny, tiny parallax. Our best measurement of Proxima Centauri's parallax is 0.76813 plus or minus 1.04 times 10 to the minus 3 arc seconds. So yes, we have the measurement and we have our uncertainty in that measurement, as always in science. But that is less than 1 arc second. And I will take a little bit of time to, if you remember that weird astronomy distance unit, the parsec. Notice this is in green, so it's for the curious. So a parsec is the distance a star would have to be away. So if I make this star 1 parsec away from the Earth and the Sun, then I would measure a parallax of 1 arc second. So it's the distance away that a star would be to have a parallax of 1 arc second. And now you can see where the term parsec comes from. Parallax, par, of 1 arc second, sec, par, sec. All right, so I promised that I'd actually give you a demonstration. So let's go ahead, and I've set some things up here in my home so you can observe parallax. What we're going to do is we have a fixed background right here, this meter stick. You may or may not be able to read the numbers on there, but I have something that we can view. So we're going to view this chopstick here that's sticking straight up. So this is our vantage point A, and I'm going to move my camera 10 centimeters that direction. And as I move it, look at where the chopstick appears to be against our fixed background. So going to move 10 centimeters, and it looks like the chopstick is moving compared to the background. So what you're observing there is the parallax. So a physical example for you to experience. Now let's look at the parallax versus the distance. So this time, burn into your brain about where that is, where the chopstick is on the meter stick. And I'll move it 10 centimeters away. And it's about right in the middle of the meter stick. I'm going to now move this. I'm gonna a little bit more than double the distance. And I'm going to repeat the experiment. So now the object is farther away. My parallax should end up being smaller. So again, I'm going to move my camera by 10 centimeters that direction. Go ahead and make a mental note of where the chopstick is on the meter stick. Move it 10 centimeters. Move it back. Vantage point A, B, baseline of 10 centimeters. And notice that it's not moving as much. In fact, it's moving by about half the displacement that we observed before. All right, so I think that's a fairly thorough treatment of parallax. Hopefully you understand the concept. If not, get on those Canvas discussions, and I'd love to answer some questions about this. See you in Unit 1, Part 3.